Now, after showing this, Einstein turned to finding the significance of the constant h, because now we have rewritten the distribution of the number of systems. These different systems can also be interpreted as particles. We saw that the distribution can be rewritten in this form: e to the minus 2h times the energy, the total energy, and if we consider more subsystems, we will have to sum all the energy of the subsystems to get the total energy E. Then we have dp1 dot 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 dqn. This is related to the distribution, and if we integrate this over the whole volume, we will get the number of systems, capital N. Now, Einstein considered the average kinetic energy per momentoid. Now, let me show you what he meant by momentoid and how to calculate the average kinetic energy. We have to integrate over the distribution that I can rewrite like this, e to the minus 2h, and then the total energy can be rewritten as the potential energy of the system plus all the kinetic energies of each single momentoid, that can be written as 1/2, and then I have some parameter alpha j, which is related to the mass of the particle or the system. Qj squared, Qj can be interpreted as the momentum, as I said, of the jth system. And then if I want the average of the kinetic energy here of, for example, the kth system, I have 1/2 alpha k qk squared here, and I have to integrate over dp1 dot 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 dqn, and I have to normalize this, so I divide by integral of e to the minus 2h v plus sum over j 1/2 alpha j qj squared dp1 dot 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 dqn. And Einstein rewrote this as the total kinetic energy, the average total kinetic energy, that he called L bar, but we also have to divide by n. N is the number of variables that we have for positions. N positions, for example, which is not in general equal to the number of particles that we have, because, for example, if we have n particles, then each particle has 3 coordinates to describe its positions. So the total number of particles multiplied by 3, for example, can describe the coordinates that we have to use, the number of coordinates that we have to use. So in this case, n is related to the number of systems or particles, if you want, but in principle it is not equal, but it is proportional. Okay, so that's why he used the word momentoid, which is related only to 1 degree of freedom. We can show that this seemingly complicated integral gives us 1 over 4h. So this means that h is related to the average kinetic energy of the overall system. Now let me show you the steps of how you can prove that these integrals give you 1 over 4h. Well, we are only interested in evaluating integrals of this kind. We have to integrate 1 over 2 alpha q squared e to the minus 2h times 1/2 alpha q squared dq. Why are we interested only in these integrals? Well, because v does not depend on the momenta, it depends on the positions, p1, p2, pn. If we consider just a conservative system, v is a function that depends only on the positions, not on the momenta. And the only meaningful integral is this one divided by integral of e to the minus 2h 1/2 alpha q squared dq. All the other integrals will simplify, and we are only left with this, and we have to integrate over momenta from minus infinity to plus infinity here as well. And if we find the result of this ratio, we will get the result of this ratio as well here, and we will find this to be equal to 1 over 4h. So the integral in the numerator can be written like this: minus 1 over 2 derivative with respect to h of the integral from minus infinity to plus infinity of e to the minus 2h times 1/2 alpha q squared dq, and then we divide by the same quantity, integral from minus infinity to plus infinity e to the minus 2h 1/2 alpha q squared dq. Now we have the same integrals in the numerator and the denominator, so we have to calculate only one integral, but that's quite easy to calculate because that's a Gaussian integral. So we know how to calculate it. We have minus 1/2 derivative with respect to h, and then the result of the integral is square root of 2 multiplied by the square root of 1 over 2 alpha h, and therefore also in the denominator we have square root of 2 pi times square root of 1 over 2 alpha h. This is just minus 1/2 derivative with respect to h of h to the minus 1/2 here, and we have to divide by h to the minus 1/2. So we get 1 over 4 h to the minus 3/2 divided by h to the minus 1/2, and when you simplify, this is exactly 1 over 4h.